We started our new unit on magnetism last Thursday, the day before we went over our test. And if you remember that far back, we defined a magnetic domain as a region in a tiny little region inside a ferromagnetic material that are represented by arrows. We're not saying that they really are arrows. We just simply represent the direction of these things by arrows. To really understand this, though, we have to know what a ferromagnetic material is. Tell me what a ferromagnetic material is.
Oh, yeah.
Go ahead.
Something that has the potential to become magnetized.
Yeah, something that can become magnetized. Something that is not necessarily a magnet right now, but can become a magnet. And what's probably the most common example of a ferromagnetic material? Iron, steel, anything that's an iron alloy. So anything that can become a magnet is a ferromagnetic material, and these domains are these tiny little regions inside those materials. If we magnify them to the point where we could see these domains, we wouldn't physically see arrows, but again, we can simply represent them by arrows. Those arrows would normally be pointing in random directions. It's a non-magnetized ferromagnetic material. There's no polarity associated with this, no north pole, no south pole, no positive, no negative, but I can induce a polarity. How do I make this become a magnet? Let's bring another magnet nearby. This time we have the domains aligned. This is a magnet. The domains are aligned already. That will cause a temporary alignment of domains in this non-magnetized material. So these domains in the blue one that are pointing in random directions, we start seeing that those domains start pointing at least more or less in the direction that the domains are pointing in that permanent magnet over here that I brought nearby. It's become a magnet. This piece of steel is now a magnet, albeit a short-term temporary magnet. Sometimes we call it a soft magnet. When I take this away, this goes back to the way that it was, more or less, although not necessarily instantly, not quite as quickly as you would see in electricity. Okay, but in the end, it would go back to the way it was before. We call it, again, that's what we call it, a temporary magnet. Yep.
I have a question about magnetism.
What's the polarity of this? It's a temporary magnet, right? It's magnetized. This is your fridge, right? This is a fridge magnet that you bring home from school with the school address on it or whatever. You put it on your fridge, and this becomes your fridge right behind the fridge magnet. What's the polarity of this temporary magnet that we've just created on a refrigerator? This is going to be the south pole. This is going to be the north pole. Temporarily, this would be the south pole, of course. This would be the north pole, although that's not a temporary thing. That's a permanent thing, right? North attracts to south. That's why magnets will attract non-magnetized ferromagnetic materials, because what it actually does is temporarily aligns the domains inside, making the side that's closest the opposite pole. Now, what's the other way we can do that? Well, we have to have a magnetic field nearby. And that magnetic field has to be in a specific direction. It has to be aligned. But it doesn't have to come from another magnet. It could come from an electric current. So what I'm going to do this time is wrap some wire around here. I'm going to hook that battery, or that wire up to a power supply, a battery, or some kind of power supply. When you move electric current through a wire, it generates a magnetic field. We'll talk more about that later on. That magnetic field can cause the domains in this non-magnetized ferromagnetic material to become aligned. So now what you've got is the same effect, but caused by the electric current. It's not electric current flowing through that. It's electric current flowing around it. Okay? Now, this goes back to your question a minute ago. What happens when I flip off the switch to take the current away from the wire? It stops inducing a magnetic field, and therefore you end up getting your domains that were pointing in the same direction to go back wherever they were before. So if you've got that Top Gear episode that you're talking about, them trying to basically pick up the cars with this magnet, how does it work? It's an electromagnet. When you flip off the electric current, the magnetic effect disappears, or at least pretty much disappears. When you flip on the current, the magnetic effect is almost instantly as strong as it's going to be. Make sense? What would happen if I took one of these magnets and cut it in half? Right, we got a south pole, we got a north pole, we got domains pointing in directions from south to north. If I cut this in half, so I have two magnets, a magnet, a south magnet and a north magnet, is that how it works? can't have a south and a north. You can have a positive or a negative, but you can't have a south and a north. We define the direction of the magnetic field, or the sorry of the domains, as being from south to north. So there has to be a south and a north. From south to north, there has to be a south and a north. All right. Here's the three laws of magnetism we talked about on Thursday. Much like the three laws of electricity, right? We got like poles repel. So north repels north, south repels south. Unlike poles attract. Positive attracts negative? No. North attracts south. And finally, the last one, we kind of have just been talking about that. North and south poles, or magnets, attract non-magnetized ferromagnetic materials. That's important. Why is it important to have that word ferromagnetic in there? What's going to happen if I bring a magnet nearby a board marker? Nothing. Magnets don't attract non-magnetized materials. Magnets attract non-magnetized ferromagnetic materials. And why does it have to be ferromagnetic? Because we have to be able to get that temporary alignment of domains, just like we have to get that temporary separation of charge with the electricity. All right, you guys have this written down from Thursday. Eh? You guys did an activity on Thursday, that would have led you to the following magnetic field diagrams. We got a north pole and a south pole, and we got a magnetic field going from north to south around like this. This looks an awful lot like this diagram that we drew in the last unit. Right, the electric field surrounding two charges. In fact, the only field line we're really missing in the second diagram is this one. If we trace these field lines around from north to south, inside they end up going from south to north. Yes, from south to north. That's the wrong direction there. Which, if we look at our domains, the domains are all pointing from south to north. So really these domains are just a reflection of which way the magnetic field points inside of the bar magnet. We're going to say, in fact, that the magnetic field points in the direction that a compass points, but it also points from north to south. So put a compass in the magnetic field, it's going to point in the direction of the field, which, as you can see in this diagram, manifests itself as being from north to south. Second picture. Recognize this from Thursday? Yeah, it's a little bit more detailed than the diagrams you drew when you did your activity on Thursday, but it's pretty much the same thing. Magnetic field lines going from south to north. They join up. Why do they join up? Because these two magnets would attract each other. And then at some point, the field lines go away from north, and they can't make it over to this south. At some point, it's easier for them to make it over to this south. And similarly, from north to south this way. And the next one. Well, north against north, we would expect these field lines to not join together. How come? Field lines join together when two things attract. And if we have north against northian, then they're going to. So the field lines have to go away from each other. They have to push each other away, right? Now here, field line would go from north to south because ultimately, I mean, it's part of the same magnet, but there would be an attraction if it was two separate things. So the field lines will go from north to south and join there. This one's going to look an awful lot like, what if we had two positives here? The electric field right there, right? But then what if we put a negative over here? It would look something like this, right? And what if we put a negative over here? It's almost exactly the same, except we're talking about magnetic fields now instead of the electric fields. Remember, please, that we're defining the direction of the magnetic field as being the direction that a compass points when placed in the field. You did the activity with these field line diagrams on Thursday where the compass pointed in the direction of the magnetic field. But we also define it as being from north to south, which leaves us with that mind-blowing conclusion that we came to on Thursday afternoon, that the Earth's magnetic field is opposite to what we typically think of it as. If you put a compass right here at the equator, that compass will point this way. That means the magnetic field points this way. That means because it points to the south, this must be south up here in Canada, and this must be north down here in Antarctica. Magnetically, the South Pole is what we think of as the North Pole, and the North Pole is what we think of as the South Pole. Geographically, Santa Claus lives in the North Pole, but magnetically, Santa Claus lives in the South Pole. Geographically, Chilly Willy the penguin lives in the South Pole. Geographically, he lives in the South Pole, but magnetically, he lives in the North Pole. It doesn't need to change anything about how we've ever done anything. Okay, if you're a Boy Scout and you are navigating in the woods, it doesn't change a thing. We think of this up here as the North Pole. As long as we're all thinking of it as the same thing, it's all good. Just understand that technically it's not the North Pole. Magnetically, it's the South Pole. And since we're talking about magnetism in this unit, we're usually going to refer to it as the South Pole. Yeah, Connor? You don't need to write this down. This is just a table from your textbook that gives us a few different magnetic field strengths. By the way, magnetic field, given by the symbol B. This is magnetic field, and the units for magnetic field are the symbol T, Tesla. Like the car, Tesla. So we're going to give you a few different magnetic field strengths. It's not because you have to know the values of different magnetic fields, but just for perspective. So you can kind of get an idea as to how this magnetic field would compare to that magnetic field. The first one that I want to show you is the magnetic field strength caused by the Earth. Now it varies depending upon where you are on Earth. In some places it's stronger than others, but it doesn't vary by that much. And on average, it's about 10 to the minus 5 Tesla. So I mentioned the other day that the Earth's magnetic field is a weak magnetic field. 10 to the minus 5 is pretty weak magnetic field. It's compared to, say, a bar magnet, which is 10 to the minus 2 Tesla. Now, every bar magnet is clearly going to have a different strength. The bar magnets that you guys used in your activity on Thursday were very, very weak. When you put them together, north against north, you could barely feel any repulsion. Or north against south, you could barely feel any attraction. But even with them being very weak, probably weaker than what you see here, they were still much stronger than the Earth's magnetic field. That's why when you brought a compass nearby those bar magnets, the compass was affected more by the bar magnet than it was the Earth. As weak as the bar magnets were, they still affected the compass more than the Earth did. Bar magnets are typically 1,000 times, 500, 1,000 times stronger than the Earth's magnetic field. A sunspot. This is, sometimes you hear about solar activity, right? Solar storms. You ever hear on the news like, oh, keep an eye out in the skies, in the northern skies tonight, and for the next couple of nights, because there's all this solar activity and we're going to see northern lights? You ever hear them say that on the news? Well, when they have these sunspots, these charged particles are released from the sun and they come towards Earth, and these charged particles are affected by the Earth's magnetic field and ultimately cause, sometimes, northern lights and southern lights as well if you live in the southern hemisphere. The magnetic field caused by these sunspots is about 10 to the minus 1 Tesla. So what, about 10 times stronger than bar magnets? About 10,000 times stronger than the Earth's magnetic field? Anybody ever had an MRI? You go to get an MRI. I've only had one once in my life, but I remember they made me fill out this big, long questionnaire, which included all kinds of things about, like, sometimes it seemed like the most ridiculous questions. Have you ever had metal in your eye? No, I haven't. Why do they ask you a question like that? Why have you ever had metal in your eye? Who cares? Why do they need to know that? They're just being nosy? Yeah. What if it's a ferromagnetic metal that you had in your eye? And you got a magnet that has a magnetic field strength of 15 Tesla, which is 10 to the 1 Tesla, which is a million times stronger than the Earth's magnetic field. Okay, you got a little chunk of iron in your eye or a little chunk of steel in your eye, okay, that might not be good because it would be quite a force of attraction with this MRI device. Listen, if you got metal in your eye, you want to stay, or ferromagnetic metal in your eye, you want to stay away from an MRI machine. But what you really want to stay away from, if you have ferromagnetic metal in your eye, is this magnetic neutron star, which has a magnetic field strength of about 10 to the 11 Tesla. Now, I don't know this. I don't know how much magnetic field would be required to do this, but I'd be willing to bet that the magnetic field strength of a magnetic neutron star is so strong that it would probably literally suck the iron out of your blood and make you suffocate. Now, here's the good news. You don't ever have to worry about that happening, because if you ever got remotely close to a magnetic neutron star, listen, you'd be dead long before you ever got remotely close to a magnetic neutron star. So the good news is you wouldn't have to worry about the iron getting sucked out of your blood because you'd already be dead. Yeah. Listen, guys, you don't need to memorize these numbers, but it is sometimes helpful when you're solving a question later on in the unit once we've done some math to know kind of what's reasonable. We get a magnetic field strength of 10 to the minus 23. That's probably not reasonable, right? Because that would be ridiculously weak. But on the other hand, if we get a magnetic field strength for a bar magnet of 10 to the 4, well, that's probably not reasonable. You don't have to know these numbers, but know at least that 10 to the minus 23 and 10 to the positive 4 aren't reasonable numbers. It helps you to identify whether you've made a mistake or not in a question once we learn to do some calculations with this stuff. Right? Finally, a little comparison here of the three fields that we've done so far last year and this year. We've got our gravitational field, which of course is caused by an object with mass, and it can be attractive or repulsive. Sorry, it can be just attractive, points toward the producer. An electric field is caused by a charge, an electric charge. It can be attractive or repulsive. It's away from the positive, it's toward the negative. And finally, magnetic field. Do you love the way I wrote this? A ferromagnetic material with aligned domains. What's an easier way, a simpler way to write what I just wrote in that cell? A magnet. A ferromagnetic material with aligned domains is a magnet, which of course it can be attractive or repulsive. It's the way that a compass points, and it's from north to south. Just as an electric field is the way that a positive charge moves away from the positive toward the negative.